In this video, I will introduce you to the normal distribution. First, let's talk about what it means to be normal. Well, at least in the sense of a distribution. A normal distribution is a symmetric, bell-shaped distribution. It's often the result of measuring continuous data, like heights, weights, or temperatures. These normal distributions can be used as a standard of comparison. We can look at where most people fall within these distributions and say, well, this range is normal. Anything above or below this range would be not normal. Now, we've looked at histograms that represented frequency distributions already, and we're going to use this as a model to see where these normal distributions come from. The histogram that you see on the left-hand side here is roughly symmetric. The left-hand side looks pretty much like the right-hand side. The tallest bar is in the center, and this is where we would find the mean, median, and mode. Now, histograms are results of taking a sample of data. If we start to increase the sample size and at the same time decrease the class width, we will take our histogram and create a histogram that you see over on the right-hand side. So here we can have the same values, but we're maybe increasing our sample size, so we're getting more data, and we're making our class width smaller. So that's why our bars are a little bit skinnier. As you see, if you think about a curve that would sit right on top of these bars, it's a little more smooth than what you would see in the previous histogram. Now, as we start to increase our sample size, we really want to keep increasing it until eventually we get the entire population. We also want to keep decreasing our class width until we actually only have one single value in each class, one single number on the number line. And again, if we continue to do that, our distribution becomes more and more smooth and more symmetric, like you see in this bottom right example. Now here you have 4 examples of normal curves. So we've taken the bars out and just have looked at those curves that would just sit along top of the histograms. Here we have 4 different distributions. They have 4 different means and 4 different standard deviations. You see they all have the same shape. They're symmetric and they're bell-shaped. You also see that your mean would be right in the center of each of these curves. Now, the problem with these curves is that they're spread out along the number line. The means are not the same, the standard deviations are not the same. All right, we'll talk about what to do with that in just a moment. Just to recap the properties of our normal distribution. These are theoretical distributions. So we're imagining what the distribution would look like if we had the entire population's data, not just the sample. Also think about decreasing our class width to a single data value. These are all symmetric and bell-shaped. The mean, median, and mode are all located in the center of the distribution. They are continuous, which means we can draw that curve without picking our pencil up. And these curves never touch the x-axis. So if you imagine we draw the curve and then they just glide along the x-axis infinitely, both to the right and to the left. Now, if we were to find the area underneath each of these curves, we would find that the area under this curve would be 1. You could also think of that as 100%. Now, to actually prove that, we would need a bit of calculus, so we won't be able to do that within the scope of this course. One thing you should also be thinking about is we will be interpreting areas as probabilities in the later sections. That's why it's important that we could think of it as a decimal, 1, or a percentage like 100%. So this picture demonstrates different areas if we look at only different slices of the normal distribution. If you notice here, the mean, or mu, since this is a population, is right in the center. As we start to slice our distribution at each of these standard deviations, we can calculate the percentage of the area that you have in that slice. Now here we go 3 standard deviations above, so we have plus sigma, plus 2 sigma, plus 3 sigma, and 3 standard deviations below the mean, minus sigma, minus 2 sigma, minus 3 sigma. Notice that if we were to total up these percentages, again, these percentages represent the part of the total area that you see. If we add them all up, we get 99.7%. Now that means that almost all of the area falls between 3 standard deviations below and 3 standard deviations above. Now again, we talked about, when we looked at this picture here, that all of the means and all the standard deviations are different. Now we want to try and standardize them, so we can put all the means in the same spot and make all the standard deviations exactly the same. And in order for us to standardize our curve, we need to use Z-score. And what that does for us is it puts our mean, or mu, at the center, or at 0, and it changes our standard deviation to 1. So this picture here demonstrates how that standardized curve relates to the curves that we saw in the previous slide. So originally our mu was right in the center, that now corresponds to 0. Mu plus 1 sigma corresponds to 1, plus 2 sigma corresponds to 2, and so forth. We see the same thing on the negative side, so minus 2 sigma corresponds to negative 2. Again, we're taking all of these normal curves and we're standardizing them so all of their means are at 0 and all of their standard deviations are 1. Now this table, which comes in your text, is used to display different areas for different Z-scores. And the table is much larger than what you see in the slide. This is just a small snapshot of it. But what it does is for each particular Z-score, it tells you the corresponding area to the left of that Z-score. So this picture here really is demonstrating what these values in the table are representing. So here you have a standard normal curve. Your mu is 0 right in the center, and here's just some Z-score that is drawn for you. Now the shading shows the area up to that Z-score, to the left of that Z-score. Those are the values that are represented here. So on this side of the table, we're just looking at negative Z-scores. Now again, your table has the negatives and the positives as well, but it's giving you the same thing, all of the area up to and including that Z-score. So let's say we wanted to find an area for a particular Z-score, and I'm actually going to pull in a larger table here for you so we could be a little more interactive with it. Get my selection tool. Okay, good. So let's say we wanted to find the area corresponding to the Z-score of negative 1.40. Now negative 1.40 is located here on the left-hand side. Since the Z-scores are always going to be rounded to the nearest hundredth, which is 2 decimal places, I find the nearest hundredth by looking at the top row up here. So this is negative 1.40, and this adds on no hundredths at all, so 0, 0. So my corresponding area would be 0.0808. Again, that would be the area up to that particular Z-score. Now that's given to you in decimal form. You can certainly convert that into percentage if you wish by moving the decimal point 2 places to the right, and that would be about 8.08%. Now we don't always have Z-scores that are rounded to the nearest tenth. Sometimes we have them rounded to the nearest hundredth. So let's say we were looking for a Z-score of negative 0.85. So again, I begin by looking at the column on the left. I go to negative 0.8, that's to the tenth. And now to go to the hundredth, to the 0.5, I'm going to just follow my finger along until I get into the column of 0.05. So think about just adding this value on to the value that you see here, and that again together gives you negative 0.805. The corresponding area would be 0.1977, all right, or roughly 19.77%. Now what I want you to do is take your tables out from your text, and we're going to use the table to find particular Z-scores or areas for particular Z-scores. So take a moment, pause, get your table, meet me back here. I'm going to show you how to do a couple of things and you'll look at some examples. Are you getting your table? I'll be waiting for you. Okay, at this point you probably have your table in front of you, and we're going to use that table to find particular z values. Now, we don't always want to find the area to the left of a z-score. Sometimes we want to find the area to the right, and sometimes we want to find the area between two z-scores. And again, this is all going to depend on the problem that we are working on. Now, here I'm just going to demonstrate what you would do if you needed to find something to the right versus to the left versus in between. And again, right now, all we're doing is practicing using the table and getting these areas. We will give some meaning to this process in the next section where we start interpreting areas probability. All right, so the first thing we're going to do is look at what we would do if we needed to find the area that is greater than a z-score or at least a particular z-score. Now again, remember the area under the curve is 1. So I'm going to draw a quick sketch of the curve, place my z-score wherever it happens to fall, and I'm going to shade in what it means to have area greater than or at least a particular z-score. Now again, the table gives you the area on the left. We want the area on the right, so we're going to take 1 and subtract the area that we get from the table. Now, if we wanted to find an area that is less than or at most a particular z-score, and again, I'm going to demonstrate what that would look like here. So here's my sketch of a normal curve. I'm going to place my z and shade in what it means to be less than or at most. Now this is just the area right from the table. See that I drew a picture that is similar to the picture that you saw or that you do see on your table that you have in front of you. Now sometimes we want to find the area between two z-scores. So this picture, we would have two different z values. We would have to look up two things from the table. So I'm going to call my first one z1 and the second one z2. And I'm looking for the area between, so I'm shading in this section of the normal curve. Now once I find the two areas from the table, I'm going to subtract them. Now the larger area would come from z2 because that is the value furthest to the right. So we'll go ahead and subtract the area for z2, and then from that subtract the area for z1 to get the area between. So I want you to use the idea of finding something greater than. You could think of this also as to the right, less than, or to the left, or between two values. Okay, hopefully you didn't see those answers yet because I wanted to hide them from you until we went ahead and found the areas from your table. So take a moment right now and let's find the area to the left of z equals negative 1.87. So go ahead, use the table that you have in front of you. We want the area to the left of that value. Now if you found that area correctly, you would find that you're just getting the area directly from the table, 0.0307. And again, it's because we're finding the area to the left, that is the area that the table is giving you. Now take a moment and find the area to the right of z equals 2.03. Again, I'll pause for a moment while you do that. And again, since we are to the right of this value, we need to subtract the area we get in the table from 1, and we get an area of 0.0212. Finally, if we want the area between two z-scores, you're going to look up these areas in your table, and again, you can pause and look that up. But once you do find those values, you're going to subtract them, and you get an area of 0.2698. Now, I hope you enjoyed your introduction to the normal distribution and how to use the table. We will be using these ideas in the next sections when we'll be looking at the probability of certain things happening.